Welcome back to the Deep Dive. So if you're currently perhaps embarking on a master's thesis or maybe preparing your doctoral prospectus, or even if you're just seeking that definitive architectural blueprint for rigorous academic inquiry, well, this deep dive is absolutely for you. We are not, indulging in casual curiosity today. We're really stepping into the engine room of science.
Indeed. And the source material you've shared, it's essentially the foundational academic syllabus, isn't it? A really comprehensive curriculum for postgraduate success.
Exactly.
It establishes a critical truth that academic writing and research are fundamentally different from pretty much every other form of intellectual labor.
Right.
They demand, systematic adherence to established concepts, techniques, and crucially, ethical integrity. That's key.
Absolutely. And our mission today really is to transform this, let's face it, dense foundational material into a crystal clear, structured guide. We want to ensure you are fully equipped, to produce research of international quality, bypassing the need to pore over hundreds of pages of methodology textbooks. We're distilling the essential knowledge nuggets right here, right now.
Okay. So when we're defining successful postgraduate research, the standards, they're universally high, and they really coalesce around three non-negotiable pillars. These determine that international quality we're talking about.
Right. Let's start with the big one, the most encompassing goal, international standards. So the primary objective here is to empower every student, you, to execute research in your specialized field that is recognized, reproducible, and importantly, respected globally. It's really about ensuring the work speaks the common language of science, isn't it? Regardless of the institution or, the country of origin.
Precisely. And that global acceptance, it's simply impossible without the second pillar, methodological proficiency. Now, this goes far beyond merely choosing a method. It requires the student, you, to demonstrate the competence to select the optimal data collection and analysis methods, specifically tailored, to the nuances of their research question.
So it's not just any method, it's the best method for that specific problem.
Exactly. What's fascinating here is the recognition that the expertise lies not in just following some single dogma, but in that strategic choice. The one that best illuminates the chosen problem.
Right.
Think about it. If a quantitative approach only gives you surface-level answers where you actually need depth, then it's the wrong choice, even if you executed it flawlessly.
It makes perfect sense. And that strategic choice, it ties directly into the third pillar, doesn't it? The one that often forms the first hurdle for publication and review. Ethical observance.
Yes, absolutely critical. This requires developing unwavering competence, really, to conduct research while strictly adhering to ethical values and, crucially, publication integrity.
And the documents are quite emphatic here, aren't they?
Oh, very. This includes the absolute non-negotiable rule against academic dishonesty. Particularly, and this is a big one, copying and pasting others' work. Academic integrity is, it's the currency of this entire enterprise. You lose that, you lose everything.
Fundamentally.
So, to achieve these three pillars, the curriculum, the source material, it mandates a deep understanding of core course content.
Right.
This spans the basic concepts, the philosophy, the methodology of science itself, alongside an appreciation of that crucial symbiotic relationship between science, theory, and, of course, the chosen research design.
And you mentioned resources, too.
Yes, we must stress the effective use of academic resources. Postgraduate work, it can't just rely on generic internet searches. That won't cut it.
No.
The researcher must identify and select information that is both effective for their argument and critically rigorously accurate. Not just everything that's out there.
Okay, so after going through this rigorous process, what skills does the researcher actually walk away with? What are the key learning outcomes that truly distinguish a postgraduate scholar?
Well, beyond just getting the qualification, obviously, you gain the fundamental ability to know and apply basic research methods and principles. That's the foundation.
Right.
But more importantly, perhaps, you develop the critical capacity to discuss the underlying concepts and the inherent problems or limitations of various scientific methods. It's not just about using them, it's understanding them deeply.
And that leads to...
But that leads directly to the most valuable skill, I'd argue. The ability to strategically decide which subject or which research method is best suited for solving a specific, clearly defined problem.
Making that optimal choice again.
Exactly. And finally, there's the practical ability, the skill to apply the specific writing format required for both submitting research proposals and ultimately publishing results in a demanding, internationally recognized academic context.
We should probably pause here, actually, and dissect that foundational methodological distinction highlighted in the material. Quantitative versus qualitative methods. Because for a postgrad, really understanding this contrast is, well, it's the first step toward methodological proficiency.
Right. Absolutely foundational. So quantitative research, this operates in the realm of statistics, numerical data, symbols. It's concerned with measurement, establishing relationships, perhaps testing pre-existing hypotheses.
So numbers, statistics?
Yes. It seeks breadth and generalizability, often asking how many or how much. Think of large-scale surveys or perhaps statistical modeling of market trends, that kind of thing.
Okay. And by contrast, qualitative research.
Qualitative is quite different. It's far more verbal, more explanatory. It requires extensive use of sentences, relies on explaining phenomena, often diving deep into context, culture, nuance, really trying to understand complex human or social issues.
So asking why or how.
Precisely. Asking why or how something happens in a specific setting. It tends to sacrifice that broad generalizability for real depth of understanding.
So a skilled researcher needs to know when to use which, or perhaps even how to combine them.
Exactly. A skilled researcher knows that choosing between them depends entirely on the research question. If you want to measure, say, the average income gap across 5 countries, that's quantitative. That's one study.
Right. Numbers, comparisons.
But if you want to understand the experience of precarious employment for, say, 5 individuals, that's qualitative. That's an entirely different methodological challenge. It requires different sampling, different analytical tools.
And making that optimal choice is what really distinguishes high-quality postgraduate work.
That's it. That's the mark of proficiency.
Okay, let's shift gears slightly and move to the philosophical core. I mean, if we're going to practice science, we really must define it, mustn't we? The source material takes us right back to the Latin root, which I think is a fantastic anchor.
Yes, it is. Science derived from the Latin scientia, meaning knowledge. Simple enough at first glance.
But academically,
yes, it's defined much more precisely. Science is a systematic and organized body of knowledge in any area of inquiry that is crucially accurate. And critically, it's achieved by using the scientific methods we'll be discussing more.
Right.
Its continuous objective, the driving force, is to create new, verified knowledge for the community. It's a contribution.
And to structure this huge enterprise, the sources categorize science into 3 broad families, right?
That's correct. 3 broad areas. The first is mathematical science. This domain examines the properties of numbers, shapes, forms, statistics.
The abstract stuff.
Fundamentally, yes. It focuses on the abstract and numerical. It provides the rigorous, logical tools that really underpin all the other scientific endeavors. Think pure mathematics, geometry, sophisticated statistical theory.
Okay. And the second one?
Secondly, we have natural science. This concentrates on naturally occurring objects or phenomena, anything from light and celestial bodies to the Earth itself, including, of course, the human body.
A very broad category.
It is, and it branches further into physical science, like physics or chemistry, earth science, and life sciences, like biology.
Got it. And the third category.
And then we reach social science. This is the domain of people and collections of people, so groups, firms, societies, economies, and their individual or collective behaviors.
So disciplines like psychology.
Exactly. The source identifies disciplines such as psychology, which focuses on human behavior, sociology, dealing with social groups and structures, and economics, which analyses markets and firms.
It seems essential for a researcher to understand which category their work falls into.
Absolutely. And also to understand that while all 3 categories use the scientific method, the level of measurement rigor, well, it varies wildly.
How so?
Well, predicting the movement of a planet that's natural science is immensely easier, more predictable than reliably predicting human political behavior, which falls under social science.
Right. Humans are messy.
They are. Social science inherently introduces complexity and measurement challenges that, well, they necessitate unique methodological approaches. You can't just apply the same tools across the board.
Which brings us to the philosophy of science. Understanding the underlying assumptions about reality seems crucial, particularly in fields like social science, where results might feel less certain. Why does a postgraduate researcher need to grapple with these philosophical positions?
It's fundamental, really. The philosophy of science is concerned with the reliability and legitimacy of scientific theories. It dictates our professional worldview, if you like, regarding what constitutes dependable knowledge.
How we know what we know.
Precisely. And given that science continuously transforms our lived reality, think about medicine, social policy, technology, understanding its philosophical limitations and assumptions is actually a substantial part of understanding ourselves and the world we inhabit. It forces us to ask, what do we assume to be true before we even begin our investigation?
That's a big question. And if the goal is objective truth, one might think there's just one single philosophical approach. But the source material outlines several quite contrasting positions. Let's maybe expand on these 5 key examples, because they really do affect how a researcher frames their methodology.
Yes, they do profoundly. We can begin with logical positivism. Now, this school of thought is extremely strict. It assumes that science must be empirically verifiable.
Verifiable through observation.
Yes. If a concept or theory cannot be proven true through objective sensory observation and measurement, then, according to logical positivists, it simply cannot be categorized as philosophy of science or legitimate knowledge. Direct observation is prized above all else.
Okay, very strict. How does that contrast with the axiomatic assumption?
Well, the axiomatic assumption approach starts differently. It assumes, as a starting premise, an axiom, that the world is inherently orderly and objective. It posits that there are natural laws just waiting to be discovered.
Like a code to be cracked.
Sort of, yes. And that if we apply the correct scientific methods, those inherent structures will eventually be revealed. It's a fundamental belief in a decipherable universe.
But doesn't that inherently disadvantage fields like, say, anthropology or critical theory, where maybe chaos, subjectivity, or power dynamics are actually central to what's being studied? If you assume order from the outset, you might miss the complexity.
That is precisely the tension, and that's exactly why other philosophies emerged. Take coherentism, for example.
Okay, how does coherentism differ?
Coherentism is less concerned with proving some external objective truth exists a priori before we start. Instead, it claims we needn't assume anything about the natural world other than that it remains consistent as we study it.
Consistent.
Yes. Knowledge, in this view, is considered reliable if it coherently and logically fits together with a broader, established body of truths we already accept. Think of knowledge like a complex jigsaw puzzle. If a new piece fits perfectly with all the existing validated pieces around it, it's considered reliable, regardless whether you directly verify the ultimate source of the whole puzzle, so to speak. It's about internal consistency.
Interesting. Then we encounter radicalism, which you also mentioned is often called reductionism.
Yes, reductionism. This is really a methodology of simplification. It's the process of reducing highly complex observations down to the simplest possible concepts by methodically breaking those observations into their component parts.
Can you give an example?
Sure. Imagine studying a complex phenomenon like political extremism. A reductionist approach might attempt to reduce its causes down to a single variable, perhaps economic inequality.
So find the simplest explanation.
Exactly. This strategy offers clarity and, importantly, testability. But the risk, as you noted earlier, is that oversimplification can mask crucial interacting factors. You might miss the bigger picture.
And finally, a significant philosophical challenge to the others: continental philosophy.
Yes. Continental philosophy offers, fundamentally, a rejection of that purely theoretical or statistical bias we often see in science. It favors understanding phenomena through the lens of real-life, subjective experience.
Lived experience.
Precisely. It suggests that truth is often found not in abstract models or equations, but in the lived contextual reality of human existence. So for you as a researcher, understanding these 5 positions is absolutely paramount. Why? Because the philosophical framework you adopt, consciously or unconsciously, dictates how you define truth, how you measure data, and ultimately how you construct your entire theoretical framework. It shapes everything.
Right.
So with that philosophical foundation hopefully a bit clearer, we can turn to the active process, academic research itself. Now, while it's generally defined as, systematically finding out what we don't know,
the academic mandate sharpens this focus quite a bit, doesn't it?
It does. Academically, it's about finding out about things that no one else knows. It's about advancing the frontiers of knowledge, maybe by examining existing topics from new angles, perhaps using different samples, or finding novel insights from, say, historical data, pushing boundaries.
And to achieve this, the entire process, according to the sources, relies on the 2 essential levels of scientific research: This systematic inquiry simply cannot exist if both theory and observation aren't simultaneously engaged.
Exactly. Two pillars holding it all up. The first pillar is the theoretical level.
Okay.
This is concerned with developing abstract concepts about phenomena, whether they're natural or social, and defining the relationships between those concepts. This is where we formulate models, principles, and ultimately build theories. It's the conceptual heavy lifting, the thinking part.
The ideas framework and the second pillar.
The second pillar is the empirical level. This is the testing ground. It's focused on testing those abstract theoretical concepts and relationships to assess how well they actually reflect observations of reality.
Seeing if the ideas match the real world.
Precisely. And the ongoing cyclical goal of the empirical level is always to refine, revise, or sometimes outright discard existing theories. The aim is constantly building better, more accurate theoretical models based on evidence.
And the necessity of balance here seems critical.
It cannot be overstated. If a researcher relies solely on observation, just gathering a mass of data without a theoretical lens to interpret it well, they're just collecting anecdotes, aren't they? It doesn't mean much.
Right. Data without theory is just data.
Exactly. And conversely, if they rely only on abstract theory, completely ignoring empirical observation, they're essentially engaging in thought experiments, maybe philosophy, but not scientific research as we understand it.
So it's a constant back and forth.
Absolutely. The scientific process, particularly at the postgraduate level, demands constantly moving back and forth between theory development and empirical testing, developing ideas, testing them, refining the ideas based on the tests, testing again.
And if you neglect one side,
the source documents are crystal clear. Your work is not considered valid scientific research. It fails a fundamental requirement.
it really is that constant iterative loop that provides the rigor, isn't it?
Yeah.
For example, a researcher might develop a theory that's the theoretical level about how, say, social media affects political polarization. Then they design a study to measure that effect empirically, the empirical level.
Test it out.
Exactly. And if the data contradicts the initial theory, maybe the effect isn't what they thought, they have to return to the theoretical level to refine the concepts, maybe rethink the hypothesized relationships before designing another empirical test.
It's a self-correcting mechanism, ideally. That's the strength of the scientific method when applied properly.
Okay, so let's assume we have our robust, balanced theory observation cycle properly in place. What does rigorous scientific research actually allow us to do? What does it achieve? The source outlines 8 primary functions. Actions we take to actively structure and analyze our world.
Right, the functions of research. We can begin with some fundamental organizational tasks. First, categorize. This involves forming a typology, basically, a systematic classification of objects, events, or concepts.
Why is it useful?
Well, it's vital for explaining which things logically belong together and how or why. It helps establish the fundamental structure of the research domain you're working in. Getting things organized.
Okay, categorize. What's next?
Secondly, we describe, this really underpins what's known as descriptive research. This function relies purely on observation to establish what is the norm. The aim is to characterize the current state of a phenomenon precisely.
Just stating the facts.
In a structured way, yes.
Yeah.
Often predicting what would likely happen again under the same circumstances. And importantly, the results of descriptive research must be provable or at least rationally guessable based on the observations.
Got it. Describe, then.
Next, we move to explain. Now, this is designed to deal with complexity. It moves well beyond simple fact gathering or description. Explanation involves making sense of the intricate political, social, cultural, contextual elements, trying to achieve a broader, often causal understanding of why things are the way they are.
So if descriptive research tells us what the phenomenon is,
Explanatory research aims to tell us why it is occurring. It delves deeper.
makes sense. What else can research do?
We must also evaluate. This requires making judgments about the quality, the worth, or perhaps the usefulness of objects or events. This can be measured absolutely against some baseline or comparatively against a rival option.
But the evaluation has to be relevant, right?
Crucially, the evaluation method must be explicitly relevant to the context and the intention of the research. Otherwise, the judgment lacks validity, it's just opinion.
Okay, evaluate. Keep going.
Following this, we compare. This seems straightforward, but it's powerful. It examines 2 or more cases, specifically highlighting both the differences and the similarities between them. This comparative method is often instrumental in leading to a deeper understanding of, say, universal patterns versus context-specific variations within phenomena.
And closely related to comparing is correlating.
Yes, we correlate. This function determines if a statistical relationship exists between two or more variables or phenomena. And if a relationship is found, the researcher must then determine the direction. Is it positive, meaning they increase together, or negative, where one increases as the other decreases, establishing connections.
Right. And the final two functions sound like the ultimate goals of science, perhaps.
They often are, yes. Predict and control. Prediction involves using strong, observed relationships from past data to forecast future behaviors or events under similar circumstances.
The crystal ball of science.
Well, a statistically informed one, hopefully. If your research, your theory, cannot predict outcomes within a reasonable margin of error, the work fundamentally fails the test of scientific usefulness in many fields.
And control.
Gaining control means understanding the causes of relationships so deeply that one is capable of deliberately exerting influence over the vital ingredients or variables within the study or system. Mastery of control allows for the reliable testing of hypotheses and, in applied fields, the development of effective solutions or interventions.
So these 8 functions: categorize, describe, explain, evaluate, compare, correlate, predict, control. They're all executed via the scientific method.
Exactly. Which, as we noted, is a standardized set of techniques for building knowledge. Its purpose is to ensure impartiality and allow for continuous improvement over time. And these methods are rigorously governed by 4 non-negotiable characteristics, the essential rules of the game for producing scientific knowledge.
Let's unpack these rules, starting with perhaps the most critical one for building reliable knowledge: replicability.
Replicability. This is the absolute bedrock. It's the assurance that any other scientist operating independently must be able to repeat your study under the exact same circumstances and obtain similar, if not identical, results.
Why is that so important?
Well, think about it. If I run an experiment on Monday and get one set of findings, and my lab partner runs the identical setup on Tuesday and gets wildly different results, what does that tell us?
That something's wrong. The results aren't reliable.
Exactly. It means our work is essentially useless as general scientific knowledge. The information cannot be trusted if it cannot be verified through repetition by others. It ensures findings aren't just a fluke or specific to one researcher.
Okay, replicability. Rule number 1. What's the second rule? You mentioned it has philosophical roots.
Yes, falsifiability. This concept, championed heavily by philosophers like Karl Popper, is arguably the philosophical backbone of modern science.
What does it mean?
It dictates that a theory or hypothesis must be testable. Crucially, it must be capable of being proven wrong.
So you have to be able to disprove it.
In principle, yes. If you propose a theory that explains everything, but can be proven by nothing, for example, if a concept is so vague or slippery that it cannot be accurately measured or tested against evidence, then it's not considered scientific knowledge.
Why is being able to prove it wrong so important?
Because falsifiability ensures that science is always moving forward. It allows us to discard weak, untestable, or incorrect ideas in favor of more robust ones that survive rigorous testing. It keeps science grounded in evidence.
That makes sense.
Third, we demand precision.
Precision. This relates directly to clarity of definition. Theoretical concepts, even highly abstract ones that are notoriously difficult to measure, things like social integration or economic anxiety, must be defined with such exactitude.
An operational definition.
Exactly. An operational definition is often required, defined so precisely that others can use those definitions to accurately measure the concepts and rigorously test the theory. Precision ensures consistency and shared understanding across research teams and different studies. Everyone needs to be measuring the same thing. Okay. Replicability, falsifiability, precision. And the fourth characteristic, it sounds like it requires some judgment. Parsimony.
Parsimony, yes. Sometimes referred to through the lens of Occam's razor, the idea that the simplest explanation is often the best.
So keep it simple.
Essentially, yes, but it's more nuanced. Parsimony demands efficiency and elegance in theory construction. When multiple explanations exist for a phenomenon and they all seem to fit the data reasonably well, scientists must always accept the simplest, most logical, or most economical explanation.
Why not the complex one, if it also fits?
Because this isn't about laziness. It's a profound principle tied to testability and falsifiability. Highly complex theories with endless concepts and variables that try to explain a little bit of everything, well, they ultimately explain nothing specific. They become almost impossible to test rigorously or falsify.
Too many moving parts.
Exactly. Parsimony forces us to focus the research effort and allocate scarce resources time, funding only to the most probable and testable theoretical paths. It prevents us from getting lost in overly elaborate, untestable webs of ideas. Okay, so the scientific method, guided by those 4 key characteristics we just discussed, replicability, falsifiability, precision, parsimony, is executed through a disciplined process. And the sources structure this process into 3 main interconnected stages: planning, methods, and the working schedule or timetable.
Right. Planning sounds like the crucial preparatory stage.
Right.
What does that involve?
It really is. Planning includes the identification and clear articulation of the research problem. You need to argue for the importance of the subject. Why should anyone care? You state the assumptions you're making going in, define the inherent limitations of your study's scope, what it won't cover. And crucially, you provide those precise operational definitions we talked about earlier, laying the groundwork.
Okay, that's planning.
Yeah.
Then comes the method stage. This is where that methodological proficiency really comes into play, I imagine.
Absolutely. This involves choosing the appropriate research model or design, defining the universe of the study, the entire population or set of phenomena you're interested in. And then, because the universe is typically far too large and expensive to cover completely,
You have to select a sample.
exactly, selecting the appropriate sample in a way that allows you to generalize back to the universe, if that's your goal. This stage also covers the specific data collection process, surveys, interviews, experiments, whatever it is, and critically, the data analysis plan.
Analysis is key, isn't it?
Oh, vital. Good data, perfectly collected data, is rendered completely useless without competent analysis. This often requires proficiency in specific tools, maybe advanced statistical programs like SPSS or AMOS, depending on the field and method.
And the third stage, the working schedule or timetable, seems practical but necessary.
Absolutely cannot be overlooked. Writing a postgraduate thesis, a dissertation, it's a major long-term commitment. It often spans years. Creating a detailed but also realistic schedule is essential for managing the sheer scale of the job and ensuring you actually make progress and complete it on time, breaking it down into manageable chunks.
Right. But the documents really stress that this entire multi-year process, all 3 stages, hinges precariously on the very first step, choosing the topic.
It really does. It's underlined heavily. A wrong choice here, selecting something you find deeply uninteresting, or something technically impossible to study, or perhaps something well beyond your current skills or resources.
It can be disastrous.
It can waste years of your time, effort, and resources. Or, quite commonly, it can lead to the eventual abandonment of the research altogether. It is, arguably, the single highest risk decision you make in the entire process.
That initial literature scan, trying to find that gap, must feel quite daunting then. How do you actually know when a topic is original enough to pass muster with demanding supervisors and, eventually, review boards? Let's dive into the 6 essential criteria the sources give for topic selection, starting with that very point.
Originality.
Originality.
Yeah.
Yes, it's paramount. The subject must be current and it must bring genuine innovation to science. The simple repetition of previously established known information must be strictly avoided. That's not research, that's reporting.
So what does original research do?
It seeks to explore the unknown. It might offer a new solution to an existing problem or develop genuinely new knowledge or a new perspective. This requires really exhaustive literature scanning beforehand, not just to see if the subject has been examined at all.
But how it's been examined.
Precisely. To determine which aspect was missed, or perhaps which context hasn't been studied, or which theory hasn't been applied. You're looking for the gaps, the missing points that need addressing. Originality is fundamentally the engine of academic contribution. Okay, originality is key. Next, and perhaps this is crucial for surviving the long haul, is interest.
Absolutely. The researcher, you must possess a deep personal interest and genuine curiosity about the subject. That intrinsic motivation, that passion, it directly affects the quality of the sustained research effort over months and years.
Keeps you going when things get tough.
Exactly. It prevents the process from becoming just a tedious chore, which often leads to people cutting corners, oversimplifying complex issues, or just giving up. Moreover, the subject should ideally also be, integrating and interesting for the wider academic community and perhaps even the general public, ensuring its relevance beyond your own curiosity.
That makes sense. We also have to assess the topic's importance. It can't just be interesting and original. It needs to matter.
Correct. The topic must contribute significantly in some way. Perhaps to science, perhaps by addressing a demonstrable social necessity, or maybe by producing a viable solution to an important practical problem.
And this has practical implications for the student too.
Often, yes. For a postgraduate student, demonstrating importance often relates directly to securing funding, or gaining necessary institutional approval, or even just getting your supervisor invested. The potential expenditure, your time, money, energy must be justified by the anticipated importance of the research outcome. If the contribution is likely to be very minor, the significant investment might not be worthwhile.
Right. The fourth criterion deals directly with the researcher's own capability. Scientific competence.
Yes, this is a reality check. The researcher must possess the necessary knowledge base and the required technical equipment or skills for the chosen subject. This includes both soft skills and hard skills.
Such as?
Well, maybe knowing a specific foreign language is crucial for accessing vital international literature in that field. That's a skill. Or, more technically, being highly proficient in particular statistical software like SPSS or AMOS as mentioned, or maybe specialized data modeling techniques or lab procedures.
So it covers methods, measurement, stats.
Yes. Required competence extends across the board: methods, measurement, statistical analysis. And if the individual researcher's capacity is, frankly, insufficient in a key area, the source material explicitly recommends considering group work, collaborating to ensure a unity of knowledge and skills, leading to a higher quality, more accurate research output. Don't try to do something you're not equipped for alone.
Good advice. Now, moving to factors perhaps outside the researcher's direct control, we need to consider field research, accessibility.
This is critical for certain types of research. If your research design requires gathering opinions from specific relevant people or groups, say, interviewing CEOs, or surveying patients with a rare condition, or if it requires physical access to a particular field site, an organization, a historical archive, or a specific location,
you need to be sure you can get in.
You must be absolutely confident you can secure that access before you commit. If the opportunity to collect the necessary data turns out to be unavailable later on, the research will inevitably be inconclusive, perhaps meaningless, and ultimately likely abandoned after much wasted effort. It's a crucial feasibility check. Can this actually be done?
Very practical point. And finally, there's a nuanced point made about sourcing. It's not simply about finding sources, is it? It's about managing the quantity effectively.
That's right. It seems obvious that it must be possible to find sufficient resources related to the research topic. You can't research something where there's literally nothing written.
But the warning is about having too many.
Yes. The source documents provide an important, perhaps counterintuitive warning. Too few resources makes the research impossible, sure. But surprisingly, too many resources can also make the work prohibitively difficult. You risk drowning in information.
Information overload.
Exactly. It can be paralyzing. The key, therefore, is efficiency. It involved collecting all potential direct and indirect sources initially, yes, but then ruthlessly selecting only the relevant high-quality parts, using an adequate amount effectively and efficiently, not just hoarding everything. This prevents that information overload from derailing the thesis writing process. Be selective.
Okay, let's try and synthesize this as we wrap up. We've established that research is a highly systematic operation, deeply rooted in specific philosophical assumptions about knowledge.
We've thoroughly established that scientific research is, well, it's a systematic journey. It's governed by quite strict rules and ethics, far removed from just casual inquiry or opinion. We learned that your underlying philosophical stance really dictates how you construct your theory.
And that theory must then be ruthlessly tested.
Yes, tested against those four crucial characteristics: replicability, falsifiability, precision, and parsimony, before you can even really begin the practical process of choosing a topic that aligns with your professional competence, your interests, and the available resources and access.
And we spent substantial time detailing parsimony, that principle, demanding we accept the simplest, most economical explanation when multiple theories seem to fit the data. Now consider this, as you, the listener, plan your own work. In an era defined by ever-increasing data complexity, by global interdisciplinary studies, and by descriptive research that specifically seeks to explain intricate political, social, and contextual elements, issues that are, by their very nature, inherently complicated. Does the classical principle of parsimony still offer the most effective path forward for genuinely advancing the frontiers of knowledge in these complex areas? Or perhaps does it risk oversimplifying the very complex issues that sophisticated descriptive and explanatory research is designed to illuminate?
A very pertinent question for modern research.
Something for you to ponder as you commit to making your own unique academic contribution.